your presentation and you can go ahead. Thanks.
Okay. Can you hear me?
Yeah, we can hear you.
Okay. Can you see my mouse? Just in...
Yes, we can see your mouse.
Okay, great. So yes, good day, everybody. Thank you very much for having me. Today, I would like to talk about the reconstruction of electron dynamics in the outer radiation belt by means of the standard and the Ensemble Kalman filter using a model that is called the verb code. The research performed in this study is part of the SFB 1294 data assimilation project funded by the DFG. And it's a collaboration between the GFC and the University Potsdam. So let me give you a little bit of a background of what we do. We are basically interested in studying the electron dynamics, the particle dynamics that generate radiation in the near Earth environment, because they have a great effect in our technology in space, but also on our life on Earth. A little bit of a side note is, for instance, energetic particles can cause damage on the electronics of spacecraft. They can disrupt GPS signals. They can induce currents that damage our power grids and submarine cables. But most particularly, they can cause anomalies and malfunctions in spacecraft in space. And a little bit of short information, for instance, during October and November of 2003, we had a very active geomagnetic period, and about 47 malfunctions on satellites were reported. So this is why this research is important. We are mostly focused on the electron populations of in the radiation belt region. The radiation belts are a two-zone structure that is basically shaped like a donut, you could say. The inner belt is mostly populated by energetic protons. And the outer belt and the inner belt is fairly stable in its dynamics, but the outer belt is very, very dynamic and can change in timescales of hours and minutes. And it's also populated by electrons. The outer belt is the focus of our research. Under certain circumstances and assumptions, we can model the electron dynamics in the outer radiation belt by means of a three-dimensional diffusion equation in terms of phase space density, abbreviated as PSD or F. And it's usually modeled in terms of radial distance, particle momentum, and particle pitch angle. We also have some particle data from satellite missions that offer several measurements at different energies and different locations in space. However, because the region, I mean, you can imagine the region we're studying is pretty vast, we need as much data as we can possibly have, and this is the most challenging task that we have at the moment. So we have data and we have a model. Obviously, we're interested in performing data simulation studies because we can reconstruct the global state of the system, and it might allow us to get information about physics processes that are missing in our models. But also, satellite companies are very interested in people who provide a forecast of the system. In the past, there were the team around Professor Spritz here at GFC implemented a standard Kalman filter, which was constructed by linearizing this Fokker-Planck equation I showed you before. And they were able to provide initial long-term reconstruction of the system and initial studies that allowed us to validate some of the physics that we know, but also showed the need to improve our physics-based models. So radiation belt plots are generally in this format. On the y-axis, we have the radial distance, and on the x-axis, the time. Color-coded is the phase space density. You could imagine some sort of electron density in space. And usually the plots are for fixed values of energy and pitch angle of the particle. Using the standard Kalman filter, our group was able to create a real-time forecasting service that is available on our webpage at GFC and provides a forecast of about 3 days of the radiation belt system. So we already have a standard Kalman filter. You may wonder, why are we interested in ensemble methods? Well, we have a big system. It's highly dimensional. So we are interested in computationally more effective methods. Additionally, we would like to avoid the linearization of the model and observation operators because we're losing information there. And our model also contains some nonlinearities that we have not been able to reproduce so far. But we have not ever done this, so this study is basically an initial implementation, just baby steps towards ensemble filtering in the radiation belt. So in order for us to assure that our ensemble filter, ensemble Kalman filter would converge to the right solution, we start very simple by implementing our ensemble Kalman filter in a system where the Kalman filter is optimal. That means that we also linearize the Fokker-Planck equation. We use also a very coarse grid, which is normally done with the Kalman filter because it's such a high dimensional problem. And we use a very simple formulation of the ensemble Kalman filter, which was shown in Gear Evanson's review of 2003 is using a simple stochastic model and a perturbed ensemble Kalman filter with perturbed state and perturbed observations. We use no inflation and no localization so that we have a simple and fair comparison between both filters. How do we set up the Kalman filter? Because it's really difficult to study errors of observations and models in a laboratory that is in space, we simply set up a standard deviation that is 50% for both the model and the observations. Now, this little guy here is the forecast state, and these are the observations. The initial state of the Kalman filter is usually set up as the initial condition of the model, which is just the steady state solution of the diffusion equation. And so in order to make these two filters comparable, we build the error covariance matrix of the model of the ensemble, as suggested by Evanson. And these matrices should converge to the error covariance matrix of the Kalman filter in the limit of infinite ensembles. So we choose a stochastic term dq that looks like this, where W is simply white noise, and RE is constructed in a similar way, but we replace this here by the observations. The ensemble of states would evolve by this equation where M is the model. And to generate our initial ensemble, we take the initial condition or the initial state that is used in the Kalman filter, and we perturb it similarly as I just described. So we already have our setup, and we want to test it in a controlled environment. So we perform a synthetic experiment. Basically, we run our model without any filtering and anything and construct a state that we will call the true state. This is this panel right here. This state is constructed by running the model with fixed parameters, and we extract data points just as a synthetic satellite would do. And then we run our model with different parameters, and we assimilate the data that we extracted into this model over here. The results of the assimilation using the Kalman filter are shown in this first row. This is the phase space density obtained with the Kalman filter, and this is the difference between the true state and the assimilation with the Kalman filter. The second row is the results with the ensemble Kalman filter using 5 ensemble members. This is the difference between the true state and the ensemble assimilation, and this is the difference between the Kalman filter and the ensemble assimilation. The rest of the rows are the same, but with increasing ensemble members. So the good news is, indeed, we get a state that with increasing number of ensembles looks more like the Kalman filter result, and with increasing number of ensembles, the difference between the Kalman filter and the Ensemble Kalman filter indeed goes to 0. So we decided that, so this means that our setup appears to be correct. So we will stick to that. And we decided that about 150 ensembles are enough to reproduce the optimal solution, the Kalman filter solution. And we went on and performed initial data assimilation with real satellite data. You can see that here in the upper panel is our satellite observations from 4 different satellites for the whole month of November in 2012. The second panel is the assimilation results using the ensemble, and the third is the results using the Kalman filter. And this is the difference between both panels, both assimilation results. And as you can see, the differences are pretty negligible. This last panel shows the geomagnetic activity during that period. Here's a big storm, and after that storm, geomagnetic activity is, or say, better say, plasma density is pretty high, and the differences are largest here, but still pretty negligible. We went further and investigated the innovation vectors of both simulations. In the upper panel, we have the innovation of the ensemble Kalman filter. In the second, the innovation of the Kalman filter, and the difference between both innovation vectors is the third panel. So what we observe from this panel is that we have strong correction at the beginning of the simulation, which means our initial condition or initial ensemble might not be the best choice, so we might have to improve that. And as shown before, also highest correction or more dynamic correction occurs after the storm. We also decided to calculate the mean innovation over the whole period. The red curve is the mean innovation of the Kalman filter, and the black curve is the mean innovation of the Ensemble Kalman filter, and you can see that they cover one another pretty well. So we are very happy about these results. And with this, I come to my conclusion. So we have successfully implemented our initial and simple Ensemble Kalman filter in a linearized model. And we have shown by means of a synthetic experiment that convergence to the optimal solution of the Kalman filter is given. Our results using real satellite data are pretty similar and pretty good. And for the future, we're very excited about looking deeper into more sophisticated techniques like localization and inflation. We would also like to test our forecast capabilities using the Ensemble Kalman filter, look deeper into parameter estimation of model bias, and correction of our model error, for instance. As I mentioned, we definitely need some improvement of our initial ensemble, and this is something that we definitely would have to look into soon. But we would also like to implement further ensemble filter techniques or even hybrid methods. And also these ensemble techniques are very suitable for to be applied in other regions of space. So this is it for me. Thank you very much.
Thank you, Angelica, for this very nice talk. And there's already one question from Lars Nerga. He asks, do you really use the Evanson 2003 square root formulation? This variant was corrected in Evanson 2004 since it had the issue to lose ensemble rank. Basically, some observations were implicitly assumed to have 0 error, and the rank of the ensemble covariance matrix was reduced by 1 for each exact observation.
I am not exactly sure. So if you mean the correction of the observation of the perturbation of the observations, we do have that. We do use that. It's just I didn't go into deep because it's we also use a similar stochastic term for that. But I don't know if that answers your question.
Well, what I meant is the 2003 variant had an error, and that was corrected in 2004 with a projection of the observation to the ensemble space. And there one has to be careful, since otherwise one can get bad results with the 2003 variant.
Okay. I mean, I can look definitely forward into that. Yes.
Yeah, you should just be careful there.
Yes, thank you.
Okay. I think there is no further question on the Etherpad page. And yeah, my questions were if you want to use inflation techniques, but I think you already answered them in your summary. So thanks again for the talk. If there are no further